Ladies and gentlemen, it is my pleasure to welcome you to my lecture about simulating chemical reactions in ESPResSo. My name is Košovan. I come from the soft matter research group at the Charles University in Prague, Czechia, and I'm a chemist by training. That is why my focus when working with ESPResSo is on chemical reaction equilibria. And I believe that most of you in my audience are actually physicists, so I can make a promise that when dealing with chemistry and chemical reactions, I will try to present it in a way understandable to non-specialists. To start with, I think it's a good idea to mention people who have contributed to what I'm going to present today, because when the same thing is done at the end of the lecture, it quite often happens that there's not enough time. First of all, I should mention two PhD students, Jonas Landsgesell and Tobias Richter, who have been working on implementation of the chemical reaction equilibria and related simulation algorithms in ESPResSo. The supervisors, Kristin Holm, Axel Arnold, and Nils Smiatek. And I should also thank the whole ESPResSo team, because I'm sure that there were many other people at ICP in Stuttgart who have contributed, even though they were not interacting directly with me. On the other hand, there is a team from Prague. There are senior researchers and postdocs, Philipp Uhlig, Pascal Herbecker, Lucia Nova, and Oleg Ruth, who have mostly contributed conceptual ideas and algorithmic development. Raju Lunkat and Roman Stanyo are a PhD student and a master student who have used these algorithms in some simulations of specific systems. And then there is Anastasia Murmiluk and Miroslav Stepanek, who are experimentalists in the group of soft matter, and they performed and designed specific experiments against which our simulations were tested and to which they were compared. So, having said that, I would like to give you an overview of what I'm going to discuss today. And this discussion includes thermodynamics of chemical reaction equilibria in general. I will start with introducing the concepts and notation, and I will try to go slowly through that in case that you are not completely familiar. And I will specifically focus on the acid-base ionization equilibria, because this kind of chemical reactions was the original motivation which led us to implementing this framework in ESPResSo. I will give an overview of simulation methods of the algorithms that we have available in ESPResSo for simulating such reaction equilibria. These include the reaction ensemble Multicolor, the constant pH ensemble, the grand canonical ensemble, and the grand reaction ensemble. In between, I will show various example results, experiments, or some ideal systems with which we will compare the simulations to show what we can do with that, but also to highlight various pitfalls that we encounter when using these algorithms, and we need to be aware of them in order to use them safely. Finally, at the very end, I want to mention some open issues and future outlooks. That comes in the concluding section, and after the concluding section, I provide a full list of references to literature that I will be citing throughout the presentation. I would like to start with describing what we can actually do when simulating chemical reaction equilibria in ESPResSo. And to do that, consider a general chemical reaction as is schematically shown here, where A, B, and some other reactants are turned to products X and Y. And in front of each of these species, we have stoichiometric coefficients denoted by nu. There is a conservation of mass in this system, which means that atoms can be regrouped in a chemical reaction. They can form different molecules, but they cannot be created or destroyed. On the level of coarse-grained modeling, it means that the number of species A, B, X, and Y can change during the simulation. However, only within some constraints that are defined by these stoichiometric coefficients. Our goal is to predict the equilibrium composition of such a reaction mixture, provided that we know its initial composition and we are given some external conditions, such as the temperature, pressure, or perhaps composition of a reservoir with which the system can exchange some particles. It's important to note that in this chemical reaction framework, we are using Multicolor algorithms, and because of that, the time evolution of our simulation, of the composition in our simulation, is actually an adjustable parameter that is a function of the type of Multicolor moves that we use and of the frequency with which we use them. And that brings me to an important point to say what we actually cannot do. We cannot do chemical kinetics. That means we cannot study the time evolution of the composition of a realistic reacting mixture. And this is because if we would like to study the kinetics, we would need to know or postulate the reaction mechanism. In practice, this is often not known, and basically the physical relevance of such results will be very questionable. In terms of what we can study with such reaction framework and why actually we should be interested in that, my answer is simple. Chemical reactions are actually everywhere in soft matter science. But if you look at most molecular simulations, they actually do not account for them. There is only a handful of simulation studies compared to a big amount of the overall simulation studies. Only a few of them we have chemical reaction directly involved. One specific reaction that we will discuss today as an example is the ionization reaction of a weak polyacid or polybase, schematically shown here, where the acidic group HA dissociates to form its ionized form A- and releases the counter ion H+, or the BH+, the protonated basic group, releases the proton and leaves out the deprotonated neutral group B. When speaking of weak acids and bases, we explicitly refer to those whose ionization state is affected by pH. And what is important for our simulations, it's not only affected by pH, but it's also affected by interactions between the molecules, and in case of charged soft matter, it's predominantly electrostatic interactions that play a role. Because we often have many interactions involved, some of them are attractive, some of them are repulsive, it is actually not easy to guess from intuition what is going to happen, or it's not easy to predict under which conditions this is going to happen. An example of that is shown at the bottom, where we see a charged colloidal particle and a polyampholyte that is a polyelectrolyte that can charge up positively when pH is high and can charge up negative when pH is low. And the goal of a simulation of such a system would be to predict under which pH this change is going to occur and how it is related to the interactions between the polyelectrolyte and colloidal particle. I will show you during this lecture several examples where you will see that very simple models actually yield surprisingly quantitative predictions of these ionization equilibria when compared to real experiments. And this is something unusual because normally coarse-grained models are not so quantitative and they rather yield qualitative predictions. To introduce the notation, let me discuss a textbook example of a dissociation reaction of a weak acid in the ideal case. And ideal here means that there are no intermolecular interactions. So we start again with this schematic dissociation reaction, and we formulate the general condition of chemical equilibrium as the minimum of Gibbs free energy with respect to the number of reactive species. And because of this constraint due to stoichiometric coefficient, this is a constraint minimization. And when we recognize that these derivatives of the Gibbs free energy with respect to to the number of individual reacting species are actually chemical potentials, we can write this down as the sum of the chemical potentials multiplied by the respective stoichiometric coefficients is equal to 0. And if we explicitly write it down for the reaction above, we have this sum of the chemical potential of A minus H plus minus the chemical potential of HA being equal to 0. Here we define the so-called ideal chemical potential. In the absence of interactions, this chemical potential is equal to the kT times the logarithm of the concentration of species I divided by some reference concentration which is chosen arbitrarily and which is related to the reference chemical potential, that means to the chemical potential in the reference state. This reference state is also chosen arbitrarily by convention, and this state has no effect on the actual thermodynamics of the system. However, it has an effect on the numerical value of the equilibrium constant of such a reaction. Here we show it on the example of the acidity constant, which is equal to the sum of these these reference chemical potentials multiplied by the stoichiometric coefficient divided by kT, and all of that being the argument of an exponential. In the case of an ideal system, this exponential of the sum of the chemical potentials can be put equal to the product of concentrations of individual species in equilibrium, multiplied by this reference concentration such that the whole equilibrium constant is dimensionless, and quite often we use an abbreviated notation, pKa being equal to minus log 10 of this Ka, and this is also one important reason why we want to make this Ka dimensionless. Well, this is the ideal case, and if we want to study non-ideal systems, interacting systems, we need to introduce corrections for this non-ideal behavior, and we can introduce this correction either by developing some kind of analytical theory or by simply explicitly simulating the interacting system. To describe this chemical reaction equilibrium, quite often we use a quantity that we call the degree of ionization, specifically for the acid-base ionization reactions, which in terms of molecular simulation is defined as the Ensembl average of the number of ionized species of the ionized form of a given molecule divided by the total sum of this species in both ionized and non-ionized forms. And in the limits of bulk system, of an infinitely big system, this Ensembl average is equal to the ratio of concentrations. That means that we can express the concentration of A minus as alpha times the total concentration of A, and the concentration of HA as 1 minus alpha times the total concentration of A. Introducing the alpha, we can then rewrite the ideal acidity constant as alpha divided by 1 minus alpha multiplied by the concentration of H plus ions and divided by the reference concentration to ensure that the whole fraction is dimensionless. And rearranging this equation, we can obtain what is called the Henderson-Hasselbalch equation, which you can find in every textbook of general and physical chemistry, that relates the ionization degree with the difference pH minus pK, K minus pH. And here again, pH is defined in the ideal case as minus log of A to the base 10 of the concentration of H plus ions divided by the reference concentration. And to give you a feeling of what this Henderson-Hasselbalch equation tells us, we look at the figure on the right. We can see that this curve, which is a solution of the Henderson-Hasselbalch equation giving the degree of ionization as a function of pH minus pK, is symmetric again around pH minus pK being equal to 0, in which case the ionization degree is equal to 1/2. If pH minus pK is much smaller than 1, that means we are on the left side of this figure. Alpha is close to 0 and the acid is practically not ionized, whereas if pH minus pK is much greater than 1 or pH is much greater than pK, then alpha is approximately 1, the acid is fully ionized and it effectively behaves as a strong acid because at this high pH its ionization degree does not depend on pH anymore. So that was the case of ideal systems, and now let me briefly introduce how the situation changes when we move to interacting systems, which is actually the interesting case that we would like to simulate. We can again start from the chemical potential shown here for on the example of the chemical potential of H+ ions, which we can express as a sum of two terms. One of them is the ideal term that we just discussed, and the other one is the excess chemical potential, and that is the part that originates from interactions. And phenomenologically, we introduce a quantity called activity that is in the same relation to the full chemical potential as the concentration was related to the ideal chemical potential. And we introduce the activity coefficient gamma as a multiplicative constant which is dimensionless and which relates the activity to concentration. So one can say that gamma accounts for the role of interactions and for the deviations from this ideal behavior, and ultimate goal of the simulation is actually computing its value. When gamma is equal to 1, that means there is no effect of interactions and the system behaves ideal. Now, if we apply this concept to polymer solutions, we find out that polymer solutions are nanoheterogeneous systems. This is illustrated on the figure on the right. When people have used fluorescence indicators attached to various positions in the polymer chain, measured its fluorescence properties and determined a quantity which they called the local pH, and observed that this local pH was different from the pH that they could measure by glass electrode, which is the pH consistent with the definition of pH provided by the International Union of Pure and Applied Chemistry, being equal to the activity of H+ ions. The local pH that they introduced here is a quantity that resembles this one, but actually what they measured and what they meant is the local concentration of the H+ ions, or more specifically the logarithm of this concentration, which is not equal to the pH as we define it in chemical thermodynamics. And I mention this just because it's important whenever you hear people talking about local pH to think twice of what they actually mean, because there are situations, and we will see them at the end of the lecture, where local pH is indeed the local chemical potential in different phases, consistent with the IUPAC definition. In here, the activity in such a nanoheterogeneous system must be the same everywhere. One can depict that or express that as a product of the local variation of the concentration, the local variation of this activity coefficient, the local correction for interactions. This is a kind of system that we would like to model in our simulations in ESPResSo. And how we do it is using a bead spring model of a polyelectrolyte that is based on, by now, standard bead spring model introduced by Bremer and Grest. And what this model accounts for is depicted in a simulation snapshot on the right. It accounts in some way for excluded volume or steric repulsion by means of short-range non-bonded potential. It accounts for chain connectivity by means of bonded potentials. It accounts for charges on the chain and also for free small ions floating around in the system. And it also accounts for the presence of the solvent in the implicit manner by treating it as a dielectric continuum with a permittivity that we usually set to the value close to the permittivity of water. When we want to model weak polyelectrolytes or reactive systems in general, we need to add one more important ingredient, and that's the chemical reaction. In the case of weak polyelectrolytes, we add the acid-base ionization reaction, which we characterize by the equilibrium constant Ka. An obvious question arises, is such model too simple to represent the complex chemical reality? And I will try to convince you that yes, the chemical reality in many situations can be hidden in this equilibrium constant Ka, and then such a simple physical model can yield very good predictions of behavior of real systems. Before doing that, though, I should introduce the algorithms, the simulation algorithms that we use in ESPResSo to simulate chemical equilibria. As I mentioned in the introduction, common molecular simulations work with a fixed number of particles in NPE or NPT ensemble, and it is a challenge to simulate with fluctuating number of particles. If you look at in simulation textbooks, you find usually one example of such a simulation method that I have listed here as number 1, the Grand Canonical Ensemble, which we abbreviate as GCMC, where our inputs are the chemical potentials of relevant species in the reservoir, volume and temperature of the system, and we have exchange of particles with the reservoir by means of inserting and deleting the particles. From these chemical potentials in the reservoir, we obtain as a result the equilibrium composition of the system, that is the amount of these particles in the system with interactions. This is nice, but this kind of simulation does not account for the chemical reaction either in the reservoir or inside the system. And therefore, another method has been introduced that is called the reaction ensemble multicolor, which we abbreviate as RXMC, where the inputs are not the chemical potentials in the reservoir, but the initial numbers of the reactive species, volume temperature, and the equilibrium constant of the reaction. In this case, the composition of such a system is constrained by the stoichiometric coefficients of the reaction, so we are working in a closed system where molecules can change their identity as prescribed by the stoichiometry, but they cannot leave the system or enter the system. This framework is in principle applicable to an arbitrary chemical reaction in a closed system, and based on the equilibrium reaction constant as an input and the initial amount of reactive species, we obtain the equilibrium composition. Number 3 comes the constant pH ensemble, which in spirit is very similar to the reaction ensemble multicolor, except that for the initial numbers of reacting species and equilibrium constant, we also provide the pH as the input. This method is designed specifically for acid-base ionization reactions, and from these inputs, we obtain as output the ionization degree at equilibrium. Last in my list is the ground reaction ensemble, which, as you can guess from the name, combines the features of 1 and 2 to simulate a system which is exchanging particles with a reservoir. So we specify the chemical potentials in the reservoir, but there are some other particles which cannot be exchanged, and at the same time there is a chemical reaction taking place inside the system. Let me start with introducing the reaction ensemble algorithm, because this algorithm, in my perspective, looks like a parent of all the others, and it introduces the key concepts that we will use later. In this reaction ensemble simulations, we do two types of Monte Carlo moves. One of them we call the configuration move, where we displace the particles, and this we can do either using Monte Carlo or using molecular dynamics or Langevin dynamics. In the end, the new configuration is accepted using the usual Metropolis acceptance criterion based on the change of potential energy between the initial and final steps. Step 2 is specific to chemical reactions. We call it a reaction move, and in this move we insert or delete particles or change their chemical identities based on the given chemical reaction. And in this case, the acceptance of the new configuration depends not only on the change of the potential energy upon this change, but also on the equilibrium constant of the reaction, the extent of reaction psi, and some other parameters that are related to the number of species of a given type in the system. Here, the extent of reaction psi can be equal to plus or minus 1. Plus 1 means that we go one reaction step from left to right, minus 1 means we go one reaction step in the other direction. When it comes to the implementation of this reaction ensemble in ESPResSo or in a simulation script of ESPResSo, consider again an arbitrary chemical reaction, but now I have selected some specific value of the stoichiometric coefficient. And if I want to set up such a reaction, I first need to define particle types, stoichiometric coefficients, and charges for each individual particle participating in the reaction. I need to define the equilibrium constant, and up to this point I do nothing else, just define my variables in Python, which I can conveniently use later. The next step is that I call the reaction ensemble module, and I initialize the reaction ensemble by providing the temperature in units of kT and two additional parameters which I'm not going to discuss and which affect the efficiency of the simulation, but not the actual result. You can look them up in documentation if you want to optimize efficiency of sampling of your reactions. Next step is that after initializing the reaction ensemble module, I define the actual chemical reaction. I can define multiple reactions if I like, but I show just one example here. First, I provide the equilibrium constant, which in here is called gamma, because gamma was the variable that was used in the original paper by Smith and Giska, who have introduced this method. Then I provide a list of the types of reactants and the stoichiometric coefficients of the reactant. I provide a list of product and the stoichiometric coefficient, again as a list. Finally, I provide the dictionary which links particle types in the reaction with their charges. And here I would like to mention that in chemical thermodynamics, the order of reactants and products, which as I specify them in the reaction, does not affect the chemical equilibrium. However, in ESPResSo, this order is important, and that is why the types and coefficients are provided as lists, as in Python or the methods in list, because we have a rule here that when we perform the reaction move, the identity of nth reactant is changed to nth product, and vice versa when going in the reverse direction. Then, if there are some particles in excess, they are deleted, and if some particles are missing, they are just created in the system at a random position. So, looking at the example above, this means that the identity of one particle A is changed to X, and the identity of one particle B is changed to Y. At the same time, one particle B is too much if we go from left to right, so it gets deleted, and two particles of X are missing, so they will be created in one reaction loop. Once this is done, I can run my simulation script, and here I show an example code when I have decided to run for 100 rounds, and within this 100 integration, with these 100 rounds, I randomly decide if I want to perform a reaction move or a Langevin dynamics integration in order to propagate either the reaction or a configuration of the system. It is not advisable to perform those two moves in a fixed order, because this in principle breaks detailed balance, although in practice we observed that the consequences are rather negligible, at least for the reactions that we have investigated. The parameter probability of reaction tunes the relative abundance of either reaction moves or the configurational moves, and this is the one that can be used to tune the sampling efficiency together with the number of integrations of each move. In each move, which I recommend to set at least to the number of 100, because otherwise you lose efficiency. Finally, I would like to say that the number of reactions that are performed within one cycle should also not be a small number, and as a good rule of thumb, we recommend setting it to the number of reactive particles in the system. So when doing this simulation, the quantity that I would like to monitor with respect to reaction is the number of particles of a given type, and this has its own command in the system module. So I'm saving the number of particles of each type in each frame of the simulation, and at the end I can compute an ensemble average of the number of particles for a given type. And that is my main result. That means the equilibrium composition of the system. So let's have a look at how we could apply this to studying acid-base reactions in the reaction ensemble. In the real experiment, what we do here in the simulation would correspond to dissolving a weak acid in pure water and measuring the pH. All of that is happening in the closed system. That means the total number of particles of the acid is constant, and it is given by the sum of the ionized and non-ionized particles, A minus and HA. The main input is the acidity constant, which is equal in the ideal case to the product of these concentrations at equilibrium. In the interacting case that we typically want to simulate, it's given by the product of activities, and both alpha, the ionization degree, and pH are the results of our simulation. That means in this kind of simulation we cannot really set the pH. We only measure it at the end of the simulation as the ensemble average of the concentration of H+ ions, making deliberately a small systematic error by neglecting the excess potential of H+ ions, but it turns out that for most soft matter systems, this systematic error is negligible compared to the effects that we would like to measure. To show you a real simulation result as an example, this is a simulation by my colleague Lucianova, where she has used an earlier reaction ensemble implementation from Philip Public, but the method is the same, and we can explain also how it works in ESPResSo using this example. On the top, you see a simulation snapshot of the polyelectrolyte chain at different ionization degrees. On the right, you can see the simulation result, which is the ionization degree as a function of pH minus pK, where the black curve represents the ideal results from the Henderson-Hasselbalch equation that is identical with what we would obtain for chain length equal to 1. And then we look at how this ionization degree as a function of pH minus pK shifts towards higher values of pK as we increase the chain length until it reaches a saturation around the chain length 50 or 100. So based on this example, we can say that the non-ideality, the deviation from the Henderson-Hasselbalch equation, increases with chain length, and it saturates at a certain chain length, suggesting that it's mainly due to the local connectivity of the polymer chain. Now, it's a good idea to look closely again at what we are actually doing in this reaction ensemble simulation. In the real world, what we could do is that we would fix the acidity constant by fixing the pKa by using one polymer, and we would measure the pH, which is controlled by a buffer or by adding a strong acid or a strong base. In the reaction ensemble simulation, we are actually varying the pKa because we cannot set the pH, and this variation of pKa affects both pH and ionization degree, which are our inputs. Based on the Henderson-Hasselbalch equation, it should look like it actually doesn't matter, because Henderson-Hasselbalch says that the ionization degree is a universal function of pH minus pK. So it doesn't matter whether I'm varying pK in the simulation or pH in the experiment, the results should be the same. However, because of this closed system, there is an intriguing pitfall that makes some things non-intuitive. The number of H+ ions in my simulation is given by the initial number of H+ ions plus the H+ ions generated by the chemical reaction, and therefore it's coupled to the ionization degree and to the Ka. As a consequence of that, if we increase the equilibrium constant or decrease the pK, then we increase both ionization degree and the number of ions, of H+ ions. But if we increase the number of H+ ions, we decrease the pH. This is illustrated in the figure in here, which may seem rather complicated to inspect quickly, and I recommend to you that you should return to it after the lecture if you like to understand this issue. But if you look here at this red region, this corresponds to high pK and at the same time high pH value, and at these high pH values we observe low ionization degrees, which seems to contradict the Henderson-Hasselbalch equation, which says that we should observe high ionization degrees of an acid at a high pH. However, this statement is only true if we also fix the pK, whereas in the reaction ensemble simulation, we simultaneously vary both. And this results in this apparent contradiction, whereas in reality this is correct, although counterintuitive. With this counterintuitive results, I would like to say again that what actually one would like to do when comparing experiments which were performed at a fixed pK and that's reported as a function of pH that was measured, is that one would like to have a simulation method where I could fix the pH and perform the simulation under the same pH as the experiment to which I want to compare. And The constant pH ensemble seems to solve the problem. I'm saying seems to solve because there is a different pitfall that prevents us from solving it completely. This constant pH ensemble has been designed specifically for acid-base ionization reactions. We can either look at the ionization of an acid or at the ionization of a base with equilibrium reaction constants of the acid and base, denoted as pKa and pKb. And the input parameters are those two components, that means the pH and the equilibrium constant. And the acceptance probability depends explicitly on the difference pH minus pK and on the extent of reaction. That means also the result does not depend on the individual values of pH and pK, but only on the difference between the two of them. The pitfall that I was mentioning at the beginning is that when I fix the pH, still the number of ions, of H+ ions in my simulation box depends on Ka, and it increases when I increase the Ka. That means, even though I have fixed the pH, my number of H+ ions in the simulation box can vary independently of this pH, and this means that pH, which I set as the input of the simulation, is not equal, and it's not even approximately equal to the log 10 of the concentration of H+ ions in my simulation box. We discuss this in more detail and demonstrate this in the tutorial number 12. It's a complication, however, it turns out that under many situations this pitfall actually does not show up if the salt concentration is not completely negligible or if the pH is somewhere in the intermediate range. It shows up when pH is very high or very low, while at the same time the salt is low, which we can formulate mathematically as maximum of pH or pOH being equal or smaller than P salt. This is the condition at which the constant pH ensemble starts to be problematic, because this inequality between pH and the number of H+ ions starts being observable in the simulation results. In terms of using constant pH ensemble in ESPResSo, the script looks very similar to the reaction ensemble. I call the SAM module, but I call the constant pH ensemble method. I provide the same input parameters as before, but before I actually set the reaction, I need to set the pH value as an input, and there is only one pH value as an input to all reactions within this constant pH ensemble. Again, I set the equilibrium constant. I provide the types of reactants and types of products. However, here only one possible combination of stoichiometric coefficients is allowed. And if you try to use another combination of stoichiometric coefficients, ESPResSo will raise an error because such a combination doesn't make sense in this context. So, to sum this up, initialization is the same as reaction ensemble, just you use a different type of the method. You provide a pH and can only provide one kind of stoichiometric coefficient. To show you again an example how powerful this method is, we have simulated two types of peptide sequences, two amphiolites. Each of these peptide sequences consisted of 5 acidic and 5 basic amino acids with different pKa values. These amino acid sequences were arranged in a block-like fashion, and we used this kind of coarse-grained model to simulate this system. And without giving too many technical details, let me just show you the main result. where we compared the total charge on the peptide as a function of pH in a very broad range. And this we compared with the Henderson-Hasselbalch equation and with several experimental techniques, and we observed that for both peptides, the agreement between simulation and experiment is very good, showing that such a simple model can very reliably predict ionization response of rather complex molecules, and it can stand a one-to-one comparison with real experiment. Now, the constant pH had one pitfall, and this pitfall was that the number of H+ ions was not actually the pH, and this could be avoided if one would introduce an explicit coupling with a reservoir, which was absent in the constant pH ensemble. And we can do that in the reaction ensemble using a special kind of reaction where on one side we have an empty set, and on the other side we have here as an example an insertion of ion pair. This reaction is equivalent to exchanging this ion pair with a hypothetical reservoir, and this reservoir can be characterized by the chemical potentials of those two ions, and these chemical potentials translate to the equilibrium constant of this special reaction, which I set as the input of the reaction ensemble simulation. It turns out that if I do this, the acceptance probability of this kind of reaction is identical with the acceptance probability of the reaction of the insertion of a pair of particles in the ground canonical simulation. So as a byproduct, I can use the reaction ensemble to simulate ground canonical exchange with the reservoir. And in the ideal case, these particles are not interacting with the reservoir. By specifying the equilibrium constant, I directly specify the product of concentrations of these particles in the reservoir. If I'm interested in an interacting system, this equality no longer holds, it's only approximate. And what I can do then is that I simulate the reservoir itself by starting with an empty simulation box, choosing the equilibrium constant of this particle insertion, and after running the simulation, I determine the reservoir composition and find out what are the concentration of ion species to which the equilibrium constant corresponds. However, if I consider aqueous solutions as my typical use case, there are never just sodium and chloride ions in such aqueous solution. Especially at high and low pH, there's going to be a substantial amount of H+ and OH- ions present, and therefore I can supplement this insertion of ion pair by additional free reactions for other ion pairs for other combinations of ions. And I should be aware that out of those 4 insertions, only 2 can be specified independently because I have 2 additional constraints in the reservoir. One of them is the ionic product of water. The other one is the overall electroneutrality. And these 2 constraints cause that when I specify 2 equilibrium constants, the other 2 can be calculated using formulas that are given in our article where we have introduced the ground reaction ensemble. Thus, we can explicitly couple our simulation to a reservoir with which can exchange ions by using those 4 exchange reactions for ion pairs. And I can supplement them by the identity exchange of individual ions based on the same rule, where I exchange H+ for sodium or OH- for chloride. And again, the equilibrium constants follow from the values of the chemical potentials of these ions in the reservoir. And while those two reactions and the whole set of 6 reactions here is actually a redundant set of reactions, that means it would be sufficient to use 3 of them, and these 3 would allow for an exchange of an arbitrary ion pair just by performing a sequence of reaction moves. Our recommendation is to use all 6 simultaneously because, depending on conditions, some of these reactions may have very low acceptance rates. And if I use just what I call the sufficient minimal set, then my simulation can become extremely inefficient, for example, at high pH or low pH. In terms of implementation in the ESPResSo script, the particle exchange reaction is used by calling the reaction ensemble and by providing the reactant types and reactant coefficient as an empty list. So, looking at that, if I can do any reaction in the reaction ensemble, I can also do an explicit coupling with a reservoir. Finally, if I can do explicit coupling with a reservoir, I should be able to simulate the system depicted on the right. That means a system which contains a reacting polymeric species, and this species cannot be exchanged with a reservoir, while there are other ions, typically the small salt ions, which can be exchanged with a reservoir. And this is a very typical situation in a polymer science, where I, for example, would have a polymer solution and it's separated by a semi-permeable membrane from a reservoir of salt solution at a given pH. It can exchange the small ions, but the polymers or colloidal particles in the system are too big to pass the membrane and they can stay only on one side of it. In such case, I have the electroneutrality constraint, which requires that the sum of the charges on cations is equal to the sum of the charges on the anions, both in the system and in the reservoir. And because there are some ions in the system which cannot be exchanged with the reservoir, I get a partitioning of other ions. They have unequal concentrations in the system and in the reservoir, such that both electroneutrality and equality of chemical potentials can be satisfied simultaneously. Specifically, this Donen partitioning of ions also affects the H+ ions, and as a consequence, I get a different pH in the system and in the reservoir, and in this case, this inequality is indeed inequality not just in the concentration, but in the chemical potential. And the local pH, described in this way, is consistent with how we define pH in the IUPAC and how we could measure it by a pH electrode. Again, it's time for some example results, and the first result I'm showing here is a Donen partitioning of ions with such a multi-component reservoir, where we have H+, sodium, OH-, and chloride. On the left-hand side, we see a proof of concept, simulation of a non-interacting system in a very broad range of pH and a very broad range of ionic strength and salt concentrations. And we see that all our simulation results presented as data points are colored to encode the pH fall on the same master curve given by the Donen partition. Here, the variable on the vertical axis is the scale Donen partition coefficient that accounts for the unequal role of cations and anions in the system. And I should mention that when we first tried simulating the system, we first simulated the interacting system as the interesting case that we wanted to investigate, and we observed the deviations from the ideal Donan behavior as one would expect, and we were happy that everything worked well. Only later we decided to test this simulation by simulating the ideal system, and it turned out that we also observed a similar kind of deviations, but in this case we know that the Donan partitioning is an exact result for an ideal system, and if we were not doing anything wrong, we should obtain this exact result from our simulations. So this told us that we were doing something wrong. We had to retract the submitted paper, and after correcting, we submitted again in 4 months. And now we are very confident that what we are doing is correct and leads to correct results. At this stage, it seems so that we are almost able to simulate a chemical reaction in the system coupled to a reservoir, because we have all these reactions available in the reaction ensemble. It's just enough to set them up, run the simulation, and we can go. However, there is a problem if pH in the reservoir is greater than 5, because in such case the concentration of H+ ions is very low, and it's not uncommon to have pH 10 or 12, so at pH 10 I have 10 to the minus 10 moles per liter of H+ ions in the reservoir, and that implies that, disregarding Donan partitioning for a while, I should observe a comparable concentration of H+ ions in my system, and 10 to minus 10 moles per liter with a normal simulation box sizes of several nanometers means that there are practically no H+ ions throughout the whole simulation. And if there are no H+ ions, then this reaction cannot run in the reverse direction, and consequently I'm not able to sample the chemical equilibrium properly. To do that, we need to add the last missing ingredient. This ingredient is added by formally adding two chemical reactions, the acid-base ionization and the identity exchange of particles. If I add them up, the net result of this reaction is that the H+ ions cancel, and the HA is converted directly to N- and sodium plus. This is equivalent to HA first dissociating and forming H+, and immediately this H+ being exchanged with the reservoir, replaced with sodium. Now, the equilibrium constant of such a reaction, which I called Ka-, is again given simply by the sum of the chemical potentials in the two reactions above. However, it does not depend anymore just on the reference chemical potentials, but it also depends on the chemical potentials of sodium and H+ ions in the reservoir. In an analogous way, I can formulate other chemical reactions, all representing the same acid-base ionization, but involving chloride and OH- ions, and again, in a similar way, I can obtain the two equilibrium constants Ka-, double dash and Ka-, and when looking at this set of four equilibrium constants, Ka single, double, and triple dash, I should recognize that only the Ka and Ka triple dash are true equilibrium constants, because they depend only on the reference chemical potentials and on the value of Kw, which are constants. On the other hand, Ka- and double dash depend on the reservoir composition through the chemical potentials of ions in the reservoir. Therefore, they are not true equilibrium constants. Putting all that together, if I want to simulate a system which has a reaction inside and it is coupled to a reservoir, I should actually use 4 chemical reactions, all equivalently representing one acid-base ionization reaction. I should use the reactions representing the exchange of ion pairs, and to boost my efficiency, I can in addition set up the identity exchange reactions. The equilibrium constants of these reactions are not independent, so I have to set them carefully in order to make my simulation consistent. But if I do that, then I obtain a simulation method that is rather robust and able to simulate such a system in equilibrium with a reservoir in a very broad range of pH conditions, including the extreme values of very high and very low pH, where the concentration of H+ or OH- can be negligible, such that I would never observe these lines in my simulation box. This brings me to the final summary and conclusions, so let me say again what we can do. We can use reaction ensemble multicolor to simulate arbitrary reactions in a closed system. We can use the constant pH ensemble to simulate acid-base ionization at a fixed pH with a small inconsistency that the concentration of H+ ions in the system is not equal to pH which I set at the input, or it's not equivalent to the pH that I set at the input. We can use the ground reaction ensemble by explicit coupling to a reservoir which is defined by composition and pH, and with a reaction inside the system. As a byproduct of these, I can do a ground canonical simulation with a special type of reaction, and all of that is well tested, either against the ideal theories such as Henderson-Hasselbalch or against real experiments on real molecules. Finally, I would like to say what we cannot do yet. And what we cannot do yet is the cross-linking reaction between polymers, as is shown here at the bottom. And the reason for that is implementation in ESPResSo rather than the limitations of the reaction ensemble algorithm, because our current implementation can create or delete particles, but there is no way of telling ESPResSo that the reaction step should actually lead to keeping both particles in the system and creating a chemical bond between them. So I suppose this problem becomes a project for a PhD or a postdoc, either in my group or in the group of Christian Holm. And with this, I would like to thank you for your attention, and I would like to remind again that if you have a PDF of this presentation, on the next slides you can see a list of references. Thank you for your attention, goodbye, and enjoy the rest of the workshop.